Okay, so 7.8 is on improper integrals. Yeah, I'm pretty sure I'm recording. Okay, uh, improper integrals. Okay, type 1. Okay, are infinite integrals. Okay, infinite integrals. And these are integrals that, these are when we have integrals that the bounds go off to infinity. Okay, for example, if I take the integral from 1 to infinity of 1 over x squared dx, okay, the graph of which is going to go like that. Okay. Um, the area, okay, uh, this one actually has a finite area, even though it has an infinite bound. Okay, it has an infinite interval. So we can actually get a finite value here. Okay, so the area under the curve, even though this thing goes off to infinity, when we start at 1, it has a finite area. It won't always be the case that it has a finite area. If it does have a finite area, we say that it converges to that finite area. Okay, and if it doesn't converge to a finite area, then we say it diverges. Okay. So how do we integrate this? Well, what I do is I use a limit, and I say the limit as t goes to infinity of 1 to t. So I kind of use t as kind of a replacement variable, and then we just say then we find a limit of whatever we get as our result. So this is going to be x to the negative second power dx, and I'm going to add 1 to that and then divide by -1. So this becomes negative x to the negative first power. Okay, evaluated from 1 to t. And then we take the limit as t goes to infinity. Let's evaluate this. This is going to be -1 over t minus -1 over 1. Okay. And so the limit as t goes to infinity of -1 over t, that just goes to 0. And then negative, that just becomes 1. So this actually equals 1. The area here has a finite area. The area is equal to 1 square unit. Okay, it's 1 square unit. So, which is kind of cool. Okay, it has a finite area. It also has a finite surface area, but an infinite volume. Very weird. Math is very weird. So if we were to rotate this, do a revolution, this is called Gabriel's horn. It's very famous. And you will talk about that more when you do Calc 3. Okay, but this guy has an area of 1 because we used the limit. And why? Because this thing goes to 0 fast enough to where we can kind of pinch it off and say, look, essentially, we're not really adding any more area after a certain point. it's inconsequential, and so the total area sums to 1. Okay. If let's write this out formally. If the integral from a to t of f of x dx exists, and t is greater than or equal to a for all x, then the integral from a to infinity of f of x dx is equal to the limit as t goes to infinity of the integral a to t of f of x dx. Okay, if the limit exists. Okay, B, if we have t to b, the integral from t to b of f of x dx exists, and t is less than or equal to b for all x, then the integral from negative infinity to b of f of x dx is equal to the limit as t goes to negative infinity of the integral of negative t, or not negative t, just t, my bad. The integral t to b of f of x dx, okay, if the limit exists. Okay, if the limit exists, we say that a to infinity of f of x dx and negative infinity to b of f of x dx are convergent. Okay, they will actually converge as union. Okay, which means that basically means that the limit is a finite value. Okay. Conversely, if the limit does not exist, they are divergent. Divergent. Okay. E, if both the integral from negative infinity to a of f of x dx and the integral from a to infinity of f of x dx are convergent, then we define the integral from negative infinity to infinity of f of x dx equal to the integral from negative infinity to a of f of x dx plus the integral from a to infinity f of x dx. And this is really helpful when we have a discontinuity. Okay, if we have a discontinuity, we can just say, well, we're just going to break it up. before that discontinuity and then after that discontinuity, and then we can just add the two integrals together. Okay, let's look at an example here. Determine if integral of 1 to infinity of 1 over x dx is convergent or divergent. Okay, is this convergent or divergent? Let's look at a graph. What was 1 over x? It was look like this. Okay, 1 over x. And we're starting at 1. We're starting at 1, 1. Okay, it's our friend from last time. Okay, and we're saying, does this area converge? Do I get an area here, even if I go off to infinity? Okay, and I think the answer is going to surprise you. Okay, we're going to have the integral from 1 to infinity of 1 over x dx, right? And so we're going to say this is the limit as t goes to infinity of the integral 1 to t of 1 over x dx. So put in our substitution variable, or substitute variable, I should say. Okay, and then we're going to integrate. Well, the integral of 1 over x, what's the integral of 1 over x?
ln x.
Natural log.
Yeah, natural log. Yeah, so this is the natural log of the absolute value of x from 1 to t. I can kind of drop the absolute value because we're starting at 1 and then we're going higher. So we're not going to get any negative values here, which is nice. Okay, so this is the natural log of t minus the natural log of 1. Okay, and the limit as t goes to infinity of this. Okay, and so natural log of 1 is 0. And so this becomes the limit of t to infinity of natural log of t. Well, the natural log function, if I look at the natural log function, it just goes on forever. It goes on forever pretty slowly, but it just goes on forever, and then it also goes up forever. So it does not have, there is no asymptote here. There's nothing that it's gonna converge to. It goes to infinity. So this thing is infinity. So the limit does not exist. Okay, the limit does not exist. Okay, and therefore, okay, the integral from 1 to infinity of 1 over x dx is divergent. Okay. Okay, it diverges. Okay, in general, if we have the integral from 1 to infinity of 1 over x to the p dx, okay, it converges for p greater than 1 and diverges for p less than or equal to 1. Okay, let's evaluate number 2 here. The integral from negative infinity to 0 of x e to the x dx. Okay, good. Okay. I'm going to take the limit as t goes to negative infinity of t to 0 of x e to the x dx. In order to do the integral, I have to do integration by parts. So again, we're using Light, okay, and we're going to go algebra first, exponential last. So u is equal to x, du is equal to dx, dv is e to the x, and v is equal to e to the x. Okay, so uv v du. So limit as t goes to negative infinity of uv x e to the x minus the integral from t to 0. This will be evaluated from t to 0. Okay, of e to the x dx. Okay, v du. Okay, and so this is e to the e to the x e to the x limit as t goes to negative infinity, t 0 to t to 0, minus the integral of e to the x is just e to the x. This is e to the x evaluated from t to 0. Okay, nice. Okay. Okay, so if I plug in 0 here, I get 0 e to the 0 minus t e to the t. Okay, interesting. Okay, and then minus e to the 0, and then this is minus e to the t. Okay, and we want the limit as t goes to negative infinity. Okay. And so 0 times anything is 0. This just goes to 0. Okay, this is minus t e to the t. This is going to be minus 1. And then this is going to be plus e to the t. Okay. I think I did that right. Yes. Let me just check my notes. Make sure I didn't do anything wrong. Nope, I think we're good. Okay. Yeah. So now we're going to try to find the limit of this thing. Okay. And so if I'm starting at 0, let me look at if I have negative infinity to 0, right? This is my interval. And what are all the values? What are all the values that would be in my domain? What type of
Negative.
Yeah, thank you, Ashley. Very good. Negative values, right? Negative values. And so if I let t be equal to, say, negative x, okay, it's really negative infinity. It's like it's a negative, it's any value here. T is going to go to negative infinity. It starts at 0 and then it marches to negative infinity. Okay. I have to treat t as if it were a negative value, is all I'm saying. So this really becomes minus negative infinity, right? E to the negative infinity minus 1 plus e to the negative infinity, right? Okay, so this guy actually becomes, if I, anything, e to the negative any power, okay, would be equal to 1 over e to the positive. Does that make sense? And so I need to drop this guy into the denominator. Okay, I'm going to drop these guys into the denominators. And it's going to become infinity over e to the infinity minus 1 plus 1 over e to the infinity. Okay, well, I know what 1 over e to the infinity is. 1 over infinity, e to the infinity is just 1 over infinity. And so that goes to 0. I don't know what infinity over infinity is. That's an indeterminate form. And so I'm going to use L'Hopital's rule to help me out here. I'm going to say with infinity over infinity, I'm going to say that this is x over e to the x. I'm going to take L'Hopital's rule. This is 1 over e to the x. And then I'm going to say, well, let x go to infinity. And so this goes to 0. So we proved that this term will go to 0 and this term will go to 0, leaving me with just negative 1 as my result. Okay, so my answer here is negative 1, which is really weird. Why would it be negative 1 for this function? Well, it all has to do with the nature of the function. If f of x is equal to x e to the x, what does that guy look like? Well, it looks like this. Okay, that's what this function looks like from 0 to negative infinity. It has this area, okay, bulges out a little, and then it starts trending to 0 from underneath. And so we get a negative area. This is equal to negative 1. It converges to negative 1. Okay. Okay, let's talk about type 2. Type 2 indeterminate forms, or improper integrals, I should say, sorry. Type 2 improper integrals, okay, are called discontinuous integrands. Okay, so type 2 here, type 1 was when we had our limits go up to infinity, or what we call infinite integrals. This one is when we have discontinuous integrands. Okay, there is a discontinuity at one of the values. Okay, and so let's define this. If f is continuous, on AB, but discontinuous, discontinuous, okay, at B, okay, then the integral from A to B of f of x dx is equal to the limit, okay, as t approaches B from the left, okay, of A to T of f of x dx. So we kind of just use a limit. Let me draw a picture. If I had a function, okay, and I had some sort of discontinuity or an infinite, it went, a cusp or something weird happening there, okay, from A to B, I could still find the area. I would just have to use a limit to, that would involve coming from uh, B from the right. So, okay, we would have, I'm sorry, from the left. So we're coming at B from the left, okay, and so we can say this is T. T is approaching B, okay? T approaches B, and so we can take a limit, okay, and that is dependent upon whether or not the limit exists. If the limit exists. And the limit is finite. Okay, B, if F is continuous on AB, this time A is not included and B is, but discontinuous at A, then the integral from A to B of f of x dx is equal to the limit as t approaches A from the right of t to B of f of x dx. Okay, if the limit, again, if the limit exists and is finite, okay, and what is the picture for this one? The picture for this one is that we're approaching B is included, but A has some sort of discontinuity, and we're approaching A from the right, and so we can still find the area. We just need to take a limit, okay, and then again, we say that T is approaching A from the right. Okay, again, if the limit exists, then the integrals are said to be convergent. Otherwise, they are divergent. Okay, and C, okay, says that if F has a discontinuity, discontinuity at C, where A is less than C is less than B. Are those strict or no? Yeah, they're strict. Okay, and both the integral from A to C of f of x dx and the integral from C to B of f of x dx, they both exist or are convergent, I should say. Both are convergent. Okay, then the integral from A to B of f of x dx is equal to the integral from A to C of f of x dx plus the integral from c to b of f of x dx. Okay, very similar to what we did before. With that said, let's do a couple of examples. Okay, number 3, let's find the integral from 2 to 5 of 1 over the square root of x minus 2 dx. Now, why is this a problem? This is a problem because the endpoint 2 is a bad value. Okay, there's a discontinuity there. Okay, I'm getting basically a vertical asymptote there at 2. But I can go very, very close to 2, almost exactly 2. I just can't use 2 as a value. Okay, I have a discontinuity at 2. Okay, so we're going to say that the integral from 2 to 5 of 1 over the square root of x minus 2 dx is equal to the limit as t goes to 2 from the right, okay, of t to the 5, integral of t to the 5 of 1 over x minus 2 square root dx. Okay. So let's do a u sub on this. U is equal to x minus 2, du is equal to dx. Okay, so this becomes the integral, okay, from t minus 2 to 3, okay, plug in my limits, of u to the negative 1/2 du. Okay, so if we add 1 to that, I get 1/2. If I divide by the if I divide by 1/2, that's multiplying by the reciprocal, which is 2. So it becomes 2u to the 1/2. Okay, evaluated from 3 to t minus 2. Okay, keep in mind that there's a limit here of t going to t from the right. Okay, plug this in, I get t times 3 to the 1/2 minus 2 times t minus 2 to the 1/2. Okay, but now having 0 here isn't a problem because we're not dividing by 0 anymore. So if I just plug in 2, okay, I get 2 radical 3 minus t times 0, or sorry, 2 times 0. I'll plug it in. It's just 2 times 2 minus 2 to the 1/2. And this whole thing goes to 0. And so I just get 2 radical 3. Okay, so that was the integral from, and what does that equal? The integral from 2 to 5 of 1 over square root of x minus 2. Okay, so essentially, what we're doing is we're finding the area under the curve. And so if I go to Desmos, I don't know what this one looks like off the top of my head, but it might be interesting to take a look at it. If I can get a keyword. So this is 1 divided by square root of x minus 2. Boom, okay. And then we're gonna go from x equals 2. Okay, so I do have a discontinuity here. You can't see it, but at 2, yeah, there is a discontinuity. Okay, at 2, if I do x equals 2, we might be able to see it better, that, this thing is basically, it gets closer and closer and closer to 2. Okay, and we want to find the area, the approximate area from 2 to 5. Equals 5. Okay, we get the approximate area here, what is the area? And so the area ends up being 2 radical 3, which is approximately, so it's this area here, it's all the area underneath this curve between these two values. Now, the reason that there's that I have to use a limit is because this thing goes off to infinity. But as it gets closer, and as y goes off to infinity, x gets closer and closer and closer to 2, so it actually does converge. So instead of going off to infinity in the x direction, this thing goes off to infinity in the y direction. And so that's why we had to use a limit. Right? Okay, let's look at another one here. What if we look at the natural log? Okay, let's look at the natural log function. ln, where's my functions? Whatever, I'm just gonna type it. Unless it's here. Oh, here we go, natural log. Natural log of x, okay? Well, let's look at our natural log function and say that we want to find the area between 0 and 1. This area, between 0 and 1, okay, first off, what type of area is that going to be? If we go from 0 to 1, everything is below the y-axis, sorry, the x-axis, and so it would be a negative area. But I want to know, well, exactly how much area is below the x-axis. Okay, from 0 to 1. Again, we have to use a limit because this is going to go off to infinity. It's actually negative infinity in this case. Okay, so let's do that. Okay. Right, number 4, yeah. Number 4 says take the integral from 0 to 1 of the natural log of x dx. So we know that x cannot equal 0 for natural log of x. Okay, so there's a discontinuity there. And so what we want is we want to take the limit as t approaches 0 from the right of the integral of t to 1 of ln of x dx. Okay, so I want to take the integral of natural log of x, and we can either use integration by parts, or we can just look on our formula sheet, okay, and integration by parts. I'll just do the integration by parts real quick because it's not too bad. Okay, u equals, okay, ln of x, dv is equal to 1. Okay, du is equal to 1 over x, and v is equal to x. Okay, so there's a dx here and a dx here. Okay, so v du is the integral, is x natural log of x minus the integral from 1 to t of, this is from 1 to t, or t to 1, I should say, okay, of x times 1 over x dx, but that's, the x's cancel. That's kind of nice. And so the integral of 1 is just x. So this is just x. So this is x times the natural log of x from t to 1 of minus of x from t to 1. Okay, since the limits are the same, I can just say this is x natural log of x minus x from t to 1. And you know, given that this is the limit as t goes to 0 from the right. Okay, so again, I could have just jumped directly to here if I used my formula sheet. Okay, so but we just plug in now. 1 times the natural log of 1 minus 1 minus t times the natural log of t okay, minus t, right? Minus t. Okay. Okay. So 1 times the natural log of 1, well, the natural log of 1, okay, the natural log of 1 is 0. So this whole thing goes to 0. Okay, so I get -1 minus t natural log of t plus t. Okay, so the limit as t goes to 0, okay, I don't have a problem plugging in 0 here because that's just 0. So this t goes to 0. Okay, I do have a problem when I plug in 0 here because I end up with 0 times the natural log of 0, which is negative infinity. So I end up with 0 times negative infinity. And what's that? Well, that's an indeterminate form. Okay, so I have to use L'Hopital's rule on this. So I'm going to say that the limit as t goes from 0 to the right of, I'm going to let this be t. I want to know what is, I don't have to put the negative if I don't want to. I just want to know what is the limit of this guy here, and then I could negate it if I wanted to. So I'm just going to say, what is the limit of t, ln of t? And now I'm going to use some algebraic manipulation to say that this is the limit as t goes to 0 of natural log of t over 1 over t. Okay, all I did was just flip that down below. Okay, and now I can use L'Hopital's rule to give me 1 over t, the limit as t goes to 0 of 1 over t all over the derivative of 1 over t, which is negative 1 over t squared. Is that right? Yeah. Okay, negative 1 over t squared. Okay, now if I flip this guy on the bottom up top, I could, instead of dividing by 1 over t squared, I could multiply by negative t squared over 1. And so that guy cancels with that guy, and I'm just left with the limit as t goes to 0 from the right of negative t. Okay, because that guy got flipped upside down. Okay, and so there's just a t. So now I just plug in, and I'm not dividing by t anymore. I'm not dividing by 0 anymore. This is just equal to 0. So that means that this guy was equal to 0, which means that this guy was equal to 0. And so I'm just left with the only number that survives, which is -1. I should probably have boxed that. Okay, so that's -1. This equals -1. And again, why would it be a negative? Because if we look at our function, the natural log function, okay, looks like so. One goes faster, 0. But yeah, and everything is negative if I integrate from 0 to 1, and the integral is -1. Okay, the area is -1. Okay, we're still doing good on time. Okay, so yeah, let's go over one last concept. Okay, the comparison theorem. Okay, suppose f and g are continuous functions with f of x being greater than or equal to g of x for x greater than or equal to a, so for some a. Okay, then we know a couple of things. Okay, we know that if the integral from a to infinity of f of x dx is convergent, okay, then the integral from a to infinity of g of x dx is also convergent. Okay, a diagram might help. It's basically, look, if I know that f of x is the bigger function and the area under f of x converges, and all of the values for g of x, no matter what they look like, are always less than f of x, so maybe this is g of x, then wouldn't these also converge? Right? Like if f of x converges, then g of x would have to converge because f of x is the bigger one. Okay. Conversely, if the integral g of x dx is divergent, then the integral from a to infinity of f of x dx is also divergent. And again, a diagram may help here. Okay. And that's if we have f of x. Okay. Okay. And then we have g of x. Well, maybe I'll do a different function. Say that we have f of x. F of x looks like, oops, f of x is supposed to be red. Naughty boy. Okay, there we go. F of x. Okay. G of x, f of x is always bigger than g of x. But if g of x diverges, okay, then wouldn't it force something that's always bigger than it to also diverge? Bring back my red. Right? If g of x diverges, now you guys are just messing with me. There we go. There we go. Okay. So again, if g of x, the smaller of the two functions, diverges, then f of x also diverges because it's always bigger. Okay, it's always going to be forced to be bigger. Okay, so if this area if the smaller area diverges or basically always grows, okay, if this thing continues to grow, the area continues to grow, they keep adding on more and more area, then anything that's bigger than it is going to also add on more and more area. Okay. Number 5. Show that the integral from 1 to infinity of e to the negative x squared is convergent. Okay, is convergent. Okay. Okay, what is this? What does this guy look like? Okay. Okay. So this is going to be e. Where's my exponents? E to the negative x squared. Okay, it looks like this guy, this bad boy. Okay. From 1 to infinity. Okay, and then let's compare it to what it would be without the x squared. Okay, what would it be without the squared? What is just e to the negative x? Let me see if I can copy and paste this. Nope. Copy. Nope. Okay. Let's just go back to my functions. Oops. Not good. E to the negative x. Okay, looks like this guy. Okay, but we're saying after 1, they're the same at 1. Okay, but what happens after 1? After 1, isn't e to the negative x always bigger? Right? I can change this color. Let's make that red. Okay, after 1, the e to the negative x is always bigger than e to the negative x squared. And one of these is a whole lot easier to integrate. Okay. Yeah, e to the negative x squared is really, really difficult to integrate. It's very, very difficult. Okay, the red equation here, very difficult to integrate. Okay, the black equation, very easy to integrate. And if we can prove that the black equation, that converges, that area converges, then we know that anything that's always less than that will also converge. Okay, let's write this up formally. Okay, and we'll just say, look, e to the negative x is greater than or equal to e to the negative x squared for all x greater than or equal to 1. Okay, so all x greater than or equal to 1. Okay, this is basically 1 over e to the x, we're saying is greater than or equal to 1 over e to the x squared. Okay. Okay, because e to the x squared is going to be bigger than e to the x. Okay, for x is greater than or equal to 1. If I plug in a number here, anything that's bigger than 1 is going to get squared. When it gets squared, it's going to get bigger. So this guy's gonna be bigger. This guy's gonna be smaller, but when I invert them, okay, what was bigger is now smaller and what was smaller is now bigger, right? So this is gonna be smaller and this is gonna be bigger. Okay. And so if we can prove that from 1 to infinity, 1 over e to the x, okay, if we can prove that this is convergent, then 1 over infinity of 1 over e to the x squared, okay, is also convergent. Okay, so that's also convergent. Okay, so let's integrate this guy and prove that that guy is convergent. So we want to take the limit as t goes to infinity of 1 to t of e to the negative x. Okay, we could do a u sub on that. Dx, u is equal to negative x, u is equal to negative dx. Okay, so this is equal to the limit as t goes to infinity of the integral from -1 to negative t of negative or e to the u, I'm sorry, e to the u. But there is a negative there, but I'm going to pull that negative outside. Negative e to the u du. Okay, because negative du is equal to dx. Okay. Okay, so now let's plug this in. The integral of e to the u is just e to the u. That's just e to the u. Okay. Evaluate. So this is negative e to the u. I'll leave the negative inside. It's just easier to deal with. Try to distribute my limits. -1 to negative t. Okay, nice. Okay. And so let's plug in our limits. Limit as t goes to infinity of negative e to the negative t minus negative e to the negative 1. Okay. So negative e to the negative t, that's going to be -1 over e to the t plus, this is just going to be 1 over e. Okay, and then we want the limit as t goes to infinity. Well, if t goes to infinity, e to the t goes to infinity, and so this thing goes to 0. And so this is just 1 over e. So the limit does exist. Therefore, the integral is convergent, and therefore, since the integral from 1 to infinity of e to the negative x is convergent and equals 1 over e, then the integral from 1 to infinity e to the negative x squared is also convergent. Okay, and equals, I don't know. Okay, I don't know what it is. Okay, but that wasn't what I wanted to know. I wanted to know, was it convergent? And it is convergent. Okay, I don't know what it is, what the integral is, because it's a very difficult one to calculate. Okay.